aluminum and fluorine. Okay, first thing you have to do when you draw an ionic compound structure is what? What do you have to do first? The Lewis dot diagram for each element. So we've got, oops, let me change up my pen. Okay, so for aluminum, how many valence electrons do we have for aluminum?
3.
All right, there's 3. And then, remember, write the plus sign in there whenever we have a reaction. We'll talk more in detail about reactions in a month or two. Plus fluorine. All right, fluorine has 7 valence electrons. So, what do we show in ionic compounds to show bonding? What do we have to draw? Arrows, right? Because arrows signify a what is taking place? Reaction maybe. A bond, but what's happening to the electrons? They're getting transferred, guys. That's the key word. So when we draw an arrow from our metal to our non-metal, we're saying that, hey, electrons are being transferred. There's a give and a take. Okay? Now, fluorine's happy. Is aluminum happy? No, why not? It still has 2 more electrons it needs to get rid of. So what's going to happen then? Another what's going to come into play? Another fluorine. So I'm going to just draw it up here because that's where I've got some space. All right, there goes that one. Then we still need 1 more, so you should have a total of 3 fluorine atoms and only 1 aluminum atom. Okay? So that's going to make an aluminum over here, brackets around it. What else has to go with that? Positive charge, right? Because ionic compounds form what? Ions. I was about to yell ionic, right? Ions, guys. Ions are formed. That's the way you should remember it. When you draw ionic compounds, you're going to show the ions. All right, then we've got 3 fluorines. Are there any dots around aluminum? No, because it gave away. It lost all of its electrons. Now, each fluorine has a what charge? -1, right? So, we've got this right here, and we've got this right here. So we're showing all of those. Now, the last thing we need to do is to write our formula. What's our formula going to be for this? ALF3. We'll talk more about formulas specifically in our next unit when we get to naming. How to name compounds, how to, this is the basics of doing compound writing, so we'll get into that more in detail in our next unit. But that's it, guys. Ionic compounds, that's how we draw those. The arrows between the elements, if you need to bring in more, you just bring in more of what you need. All right, and then you just show it there on the right-hand side of our big arrow, showing that a reaction has taken place. Pretty easy? Absolutely. Remember, there's a transfer, there's a give and a take that's taken place there. All right, so page 2, continuing, guys, now on to covalent. This is one that we're going to use a lot this year. We will draw more covalent structures and covalent bonds than we will ionic. Okay, ionic we'll spend a little bit with, but covalent's where the money's at, because when we get to tomorrow and Monday, we will start talking about Vesper. That's all dealing with covalent bonds only. So, what's the big difference between covalent and ionic in terms of electrons? One word. What's happening with the electrons in an ionic bond? We talked about yesterday. Transferring. So covalent bonds are sharing, guys. That's the key there. Highlight it. Write it in big, bold letters. Something so that you know the difference. Okay? They are sharing their electrons. Why? Because they have high electronegativity values. How we can identify covalent bonds from ionic bonds is that they are usually between 2 nonmetals. Okay? Where are the nonmetals located on the periodic table?
Far right.
Yeah, far right. To the right of the metalloid staircase. Except for one element. There is one element that is a nonmetal that is not to the right. Hydrogen, guys. Hydrogen is the exception. It acts and behaves like a metal, so it's over there in group 1. But if you notice on your periodic table, it's actually not connected to group 1. It's kind of floating above it. Okay, because it's a non-metal. All right, it's the only non-metal that is not to the right of the metalloid staircase. All right, so they share their electrons because they all have high electronegativities. What is electronegativity again? Review from Unit 3. Pause for just a second. So, high electronegativities. What does electronegativity deal with? You got to know this term. All right. Electronegativity deals with bonding. So in covalent bonds, these elements have high electronegativities because they want to bond. They want to hold on to their electrons. Again, nonmetals are to the right. What type of valence electrons do they have in nonmetals? High valence electron numbers or low valence electron numbers? High, right? Because they're to the right, they're closer to 8, which is what they're trying to get to. Now, sharing of electrons, it can be equal, which is nonpolar, or unequal, which is polar. We'll talk more about polarity here in a little bit. Okay? So, covalent bonds, like ionic bonds, guys, result in a more stable compound because they meet the octet rule. But the means are different. Ionic, what are they doing with their electrons? They are being transferred. Covalent, they are sharing. Okay? They are sharing. There may be an unequal sharing or an equal sharing that's taken place. So here's an example. 2 hydrogen atoms. All right, valence shells will overlap, so the electrons then are shared, and that's what we can see right here. You've got each of them has 1. All right, when they come together, now they have 2, which hydrogen, bless you, is the only exception. It's going to have 2 electrons to bond. Everything else will get up to 8. All right, but you can see that they overlap their shells, which allows them to share those electrons. All right. It's okay to laugh at the jokes, folks, okay? It's okay. They're hilarious, all right? Ionic bond, taken, not shared. Come on, James Bond. All right, anyway, let's start talking about drawing those bonds, all right, those covalent bonds. Very, very similar process to ionic bonds. So example number 1, guys, chlorine and fluorine. What do you think the first thing is that we have to do? And then do what with those valence electrons? Okay, before we share them, dot diagram. Yeah, we got to draw our dot diagrams, folks. So we've got chlorine. Oops, that's my laser pointer. Chlorine plus fluorine. So same initial process as ionic bonding. Okay? How many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. What about fluorine? Oh my goodness, 7. What group are those both in? Oh good, the halogens. Alright, but the big difference here now, with ionic bonds, what did we draw with the electrons? An arrow, right? And that signified a transfer was taking place. What we're going to draw here is not an arrow. We're going to circle the ones that are by themselves. We're going to just draw a line to link them. So there's just going to be a line between our elements to show that, hey, they're being connected. There's not a transfer. Not one is giving, the other one is taking. All right, so our new compound is going to look like this. We've got chlorine. We've got fluorine. We have a single line between them. Okay? Then we're going to show the rest of their dots that they had as well. Anytime you see a line between elements, that means you have a bond. How many electrons are in that bond?
2.
Yeah, 2, okay? Make yourself a side note. There's 1 here from chlorine, and part of it's from fluorine. We just represent that with a single line, okay? So, make yourself a note. A line equals a bond, which equals 2 electrons. Line equals a bond equals 2 electrons. If I had more than 1 line between an element, if I had 2 of them, how many electrons would there be? 4. If I had 3 lines, there would be 6, right? Each line, guys, represents 2 electrons. That's a big idea. That's something big that we're going to come back to when we start doing molecular structures on either tomorrow or Monday. All right, let's take a look at the next one. Hydrogen and fluorine. Hydrogen and fluorine. How many valence electrons does hydrogen have?
1.
Excuse me, it's got 1. Fluorine has?
7.
Okay. So fluorine needs how many electrons? 1. Hydrogen needs how many?
7.
Does it need 7?
It needs 2. 1.
It needs 1 more, guys. Hydrogen, remember, only is going to be satisfied with 2 electrons in its valence shell. Why? Think about it. What is our electron configuration for hydrogen? 1s1. Well, if it got 1 more electron, what would be its configuration? 1s2. Guys, how many electrons can the first energy level hold? If you can't remember this, go back to our 2n squared. 2, put a 1 in there, squared. What's 1 squared? 1 times 2 is? The first energy level, guys, can only hold 2 electrons. Therefore, hydrogen is only ever going to have 2 electrons around it. Meaning, hydrogen, which we will use a lot, especially when we get into organic chemistry, okay, it's going to only have 1 line next to it. It will never have more than just a line in a bond. No dots around it, and just 1 line between hydrogen and another element. All right, because hydrogen only can hold up to 2 electrons in its energy level. Because the first energy level can only hold up to 2 electrons. So we've got hydrogen. We're going to draw a line to fluorine. Will fluorine have any other dots around it? Yeah. Absolutely. It's going to have the other 6 that it had before. So now, if we take a look, something I forgot to do with the first example, if we were to cover this up, all right, so what I'm going to do here, I'm going to get fancy, I'm going to just cover this up right here. We're going to take away fluorine. How many electrons does chlorine have around it there in that first example? 8, right? It's got 2, 4, 6, 8 because it's in a bond now. It had 7 valence electrons by itself, but because we have a bond, there's now 8 that are attached to it. If I go back here, I'm going to do the same thing with chlorine. Cover that up. How many does fluorine have? 2, 4, 6, 8. What's the magic number I'm looking for? 8. Be within that bond, guys, because they're sharing, they each now have 8. So there's your check to make sure that you've done it correctly. If we take a look down here, cover up fluorine. Hydrogen has how many? 2. Is that okay? Absolutely. Hydrogen's only going to have 2. If I cover up hydrogen, how many does fluorine have? 2, 4, 6, and then there's 2 in there, which is 8. All right? You guys try bromine and iodine. Really quick. Oh my goodness, what in the world is that? Oh yeah. Bromine, iodine, guys, their dot structures are going to be very similar because they're both halogens. They both have 7. So this is very similar to the first example that we had. Draw your lines between them and then show them over here. Oops, it's not bromine, it's iodine. And then they each have the other 6 dots around it as well. Make sure, this is something I've got to look into. All right, on your Regents exam, when they ask for dot structures, you need to make sure you show the dots. Okay? Make sure you show all of those other dots. Otherwise, you could lose points. Okay, now we'll talk about bond polarity. All right, this is on page 3, and it'll carry on into page 4 as well. We've alluded to it already. We've talked about it, guys. Covalence, we're talking about sharing. All right, equal sharing, all right, means that you have a nonpolar molecule. All right, but when you have an unequal, you have something else that takes place. It all comes back to the difference in electronegativities. Where do you find your values for electronegativity values? Table S. So you're going to need table S, folks. You're going to be doing the difference between the 2 electronegativity values of the elements that you're looking for. Okay? Most of the time, they are shared unequally. Okay? Meaning that electrons spend more time around the more electronegative atom. So when we talk about polarity, guys, the one that has the most electronegative, the higher electronegativity value, it's going to be the more negative atom. You probably want to jot that down in your notes. The more electronegative atom, that's going to get your negative charge. Okay? So this one causes it slightly negative, and one atom to be slightly positive. So the one that's slightly negative is going to be the higher electronegativity value. The one that's slightly positive is going to be the lower electronegativity value. Because remember, guys, electronegativity is about pulling in electrons through bonding. So the higher the value, the more it really wants those electrons. It's like the big dog that I showed you before. The one that's stronger, it's going to pull on those electrons more. This is what we call a dipole moment. It's not dipole. Okay, when you guys are doing vocab, maybe you thought it was dipole. No, it's dipole. Okay, di means what? 2. Okay, pole means you've got 2 opposite things. Think about poles of the Earth, right? You got the North Pole and you've got the South Pole. In an atom, or not an atom, in a molecule, in a bond, one end is going to be slightly positive. Really, the symbol that they show is this, like this. It's a weird Greek symbol, okay? I think it's a lowercase gamma, I think is what that is. And one that is slightly negative. So you've got this, it looks like that. But they're two oppositely charged poles. So one's going to be slightly positive and slightly negative. Okay? Nonpolar covalent. Okay? That means they are being shared equally. Make sure you have that highlighted or jotted down. Nonpolar means equal sharing. Okay? Nonpolar is equal sharing. A lot of times it's going to be two of the same atoms. Okay? Two of the same atoms. There are certain ones, certain molecules that you're going to have memorized. Okay? When we get into Vesper stuff tomorrow or Monday. Electrons are shared equally. There will never be a dipole moment because they are nonpolar. Okay? Nonpolar means no poles. All right? So if they are nonpolar, there is no dipole moment. If they're polar, what does that mean there's going to be? There's going to be a dipole that forms. Okay? And that's what we talked about first with the polarity. Okay? Polar bonds, they are unequal sharing. Nonpolar, they are equal sharing. That's what you've got to know. Now, there's a table. Bottom of page 4. These are kind of arbitrary values, meaning that they don't really matter. They can change depending on different textbooks I've seen have been slightly different. These are the numbers that we're going to go with here for the difference in electronegativity. Okay? If your difference in En is between 0 and 0.4, or if it is 0.4, okay, it's going to be considered nonpolar covalent. If it's greater than 0.4 up to 1.7, it's going to be polar covalent. And if it's greater than 1.7 difference, it's going to be ionic. However, there might be some exceptions. What do we figure out, guys, when we're talking about covalent and ionic? What's the first thing we look at between ionic and covalent? Ionic is what? It is a transfer electron, but what makes up ionic bonds? What type of elements? Metal and nonmetal. Okay, so ionic is a metal and a nonmetal. And covalent is between what? Yeah, it's two or more nonmetals. All right? So, there are some exceptions where you've got covalent bonding taking place and the difference in electronegativity is greater than 2. Okay? But don't let that freak you out. If it's two nonmetals, it's going to be covalent. If it's a metal and a nonmetal, it's going to be ionic. Again, these are arbitrary numbers, meaning that there's always going to be some exceptions to the rules. All right, they're just numbers that we assign to make it a little bit easier for us. All right, so keep track of this. Know those numbers. Know the differences between them. Okay? What I want you guys to do, I want you to answer / define the terms at the bottom of page 3 and top of page 4.